Hello, we are going to wrap up chapter 14. I am not exaggerating when I say that I have just spent 3 hours picking the problems for this chapter 14 wrap up. There is a lot of material in this chapter, as I'm sure in 3 days worth of lecture you have gathered. In my search for problems and realizing that one of the examples that was worked out in the notes lacked some data, I, along the way, found some extra worksheets for you to practice, and those are located under announcements on our Sakai website. So that'll give you even more practice. But what I'm going to do is I'm going to do a problem using the Arrhenius equation, which we really did not do in class. So you've got one in your notes on pages 38 and 39. You've got a problem using this equation worked out for you. I am going to do problem number 1464 from the textbook, which uses this same equation. And then I'm going to get into some ACS problems, and then I'm going to do more on mechanisms, and I'm going to do a combination problem with initial rates and mechanism. I'm going to revisit one of the questions, number 16, that we did in class from the practice at the end of chapter 14. And so let's go ahead and get started because we got a lot to do. Okay, this is the one form of the Arrhenius equation. What has been left off of this equation is the y-intercept. In this problem on pages 38 and 39, they are asking you for the energy of activation. That is also true in your textbook for number 64. So one other note before I get into it is this equation looks a little bit different than the one in the book. And the difference is two things. And the reason that this number is here and not in the book form is that we're using a log in this form. And in the book, they're using natural log. So the 2.303 comes from the fact that that's different. And I believe the one in the book has K1 over K2 and T2 minus T1. You're going to get the same answer regardless of which form you use. Now, in the ACS, at the top of page 58, they do an example problem using the Arrhenius equation, but they don't do a practice problem. So I'm assuming that you need to know this, so that's why I'm putting it in the wrap-up, and because we didn't go over it in class. So make sure you look at this one, and now let's do 64 to give you one more practice on that. And then those worksheets probably very well do have some others as well. All right, number 64, it tells us to it gives us some information. It's a decomposition of nitric oxide, and it tells you that it is second order with a rate constant. Now, the second order part really doesn't matter, but they give you two rate constants, okay? So K1 is given in the problem, and it is 0.0796, and that is m to the minus 1 seconds to the minus 1 at 737. Celsius. And then they give you a second rate constant, and that is 0.0815. Erase that other little dot there. Okay. Same units at new temperature 947, and same as the problem in the notes, it wants you to calculate the activation energy. So if you were being asked to calculate the activation energy and you are given two rate constants and two temperatures, then this is the equation you're going to use. Now the one in the ACS at the top of page 58 actually asks you for the ratio of the rate constant. So on that problem, let me just kind of put that right here, you're actually solving for K2 over K1. But anyway, they go through it step by step at the top of page 58 in the ACS book. All right, so let's plug our numbers in for the problem in the book, and you'll see this is pretty much a plug and chug. So I am going to take the log of 0.0815 divided by 0.0796. 0796, and that is equal to EA over 2.303 times R. Now the R you're going to want to use is the 8.314 R because that's in joules. Joules per, I believe it's mole K. Okay? Joules per, let me just double check that. Joules per mole. But that's how you're going to get joules out of this, and that's what energies are measured in joules. Okay? That's on the bottom, and then you've got this whole second term multiplied times this one, and that is times, okay, 1 over T1, which would be 737 plus 273. These have to be in Kelvin. Anytime you're using the gas law constant, your temperatures have to be in Kelvin. Minus 1 over 947 plus 273. I'm learning how to read. 947 plus 273. Okay. Close brackets, multiplied times this term here. Let me do a little erasing to make this a little more, less crowded. Okay. So now we're going to simplify, right? And so it's going to be, when I take the log of this, these two things here, I get 1.03 times 10 to the minus 2 equals EA over, when I multiply the 2.303 times 8.314, I get 19.15, and essentially that's your joules, times, okay, I'm going to put times star, and star is equal to, when I take this minus that, I get 1.7 times 10 to the minus 4. Right? So let me rewrite this. Okay, so 1.03 times 10 to the minus 2 equals EA over 19.15. Again, got that by multiplying 2.303 times the 8.314 times 1.7 times 10 to the minus 4. All right, dividing both sides by this term here, I get 60.6. 60.6 equals EA over 19.15. Solving for EA, I get 1.15 times 10 to the third joules, which is 115 kilojoules. It doesn't seem right. Shouldn't be, hold on. Be 1.15 kilojoules. All right, so plugging into the Arrhenius equation, pretty much a plug and chug. Use your R of 8.314. Temperatures need to be in Kelvin. Before we take a quiz on this chapter, I will have the handout with the formulas you will have for the ACS, and I will give that to you ahead of time. Okay? I'm going to pause and get set up for our next question. The next thing I want to do is revisit the question that we did that was a non-numbered question, the AP question. Well, in fact, that question is number 80 from your textbook. So we're going to just look at the those mechanism steps again and talk about this multiplying a step by a coefficient, which we did in number 16 in the lecture. The last question we did in class. We had to multiply a step in the reaction mechanism to get all the intermediates to cancel out. So we're going to do that in this question as well, which we should have done in class. Now, the advantage to number 16 was, which is also number 86 in the textbook, is that they gave you the overall equation. In this question, number 80, the unnumbered question, they did not give us the overall equation. In fact, we had to come up with that. So having the overall equation kind of gave us a little hint that we needed to do that multiplying. But anyway, let me go ahead and rewrite these three steps for the mechanism. And we'll go through that very first part where we are having to come up with the overall equation. All right, so this is what's given. All right, and we have to come up with the overall equation. Now, we correctly identified the intermediates as HOOBR, Huber, because it's produced and then consumed, but another intermediate is the HOBR, and the problem is that you produce two here, but you only make one here, or you only use one here. So we're going to multiply this final step in the mechanism by 2 so that I get that intermediate to cancel out, right? But that's going to make everything else 2 as well. So I'm going to use the eraser so I don't have to, it'll get too confusing if I write it again down here. So we're going to take this and we're going to put 2's in front of everything. Okay. And so 2, 2, 2, and 2. So now we'll add it all together. All right. And so we have 2 intermediates here. I'll put that down here. HOOBR and HOBR are intermediates. Okay. I'm just double checking what else was asked in this question. Now, they also told you, the same as what we had in the question in the lecture, is they gave you the rate law and it asked you which step was the slow step. So, and remember that was the first step because the first step agrees with the rate law. We are going to do several more like this in this wrap up, where you're having to look at mechanisms and slow steps and rate laws, all at the same time. All right, so let's just go ahead and do this. These cancel and these cancel. Okay. Well, if I do that and add it all up, I end up with 4 HBr plus O2 gives us 2 H2O plus 2 Br2. Now, unlike the AP question, this number 80 in the book actually does give you the overall equation, and this is the correct overall equation. So that's what we had to do in order to make this work, and it's okay to take a step in a mechanism and multiply it by a coefficient to get rid of intermediates so they don't appear in your overall equation. Okay? All right, I'm going to pause again and get ready for some ACS questions. So get that book out. All right, the questions that we're going to do from the ACS book on this material are the following. Number 6 on page 61. We're also going to do number 7 on that same page. And we're going to do number 26 on page 65. Now, I have put 2 questions in an announcement, I believe, and changed the quiz calendar. And those are numbers 16 on page 23 and number 23 on page, those page numbers don't make any sense. Hold on. It's all from the same section, so the page numbers should be consistent. All right, so let's see what we got going on here. All right, that's page 23. Number 16, number 23, page 64, and number 16, page 63. I have to double check on the what I put online about that. Okay, we omit these for quiz on chapter 14, and they would be added to chapter 15. Okay. All right, because remember when you take the test, you've already covered all the chapters. All right, number 6 on page 61 says, the activity of a radioisotope is 3,000 counts per minute at one time, and 2736, we'll put counts per minute, at 48 hours later. And the question is, what is the half-life? All right, well, one thing you have to realize is that radioactive decay is first order. Again, we will do a little bit of nuclear chemistry at the end of the course, so you would have encountered that. But this question, along with these other two, are an application of the integrated rate law. And as we discussed in class, half-lives are just a special case of the integrated rate law. So we're going to need the integrated rate law for first-order reactions, which is the following. Okay, get my stuff in front of me here. So we've got for first-order reactions. First of all, why do I need this? Why do I need the integrated rate law? Why can't I just solve for this? Well, for first-order reactions, T1/2 is equal to 0.693 over K. It does not have a concentration in it. First-order reactions are the only ones that have a half-life that is independent of concentration. That was an ACS question in this section. But I don't have the K. So I am going to use the integrated rate law to get the K, because what I have here is essentially two different concentrations in time. So anytime you have different concentrations in time, you're going to be using the integrated rate law. All right, so the ln of the concentration at time t, so that's going to be 2736. We're going to look at this as our initial concentration. So it would be this in the integrated rate law expression, and this is, I think the zeros on the outside at time t. Okay? Yeah, zeros on the outside. So erase that up. Erase it too much. Okay. Equals minus KT, now T is 48 hours, and the answers for this question are in hours, plus the natural log of the initial concentration. So this is the integrated rate law for first order reactions. Okay? This little guy out of the way. All right. So, just collecting terms, doing my natural log on the calculator and so on, I get 7.914 equals minus K times 48 plus 8.006. Right? So when I subtract both sides, 8.006 from both sides, I get negative 9.2 times 10 to the minus 2 equals minus K 48. So the negatives disappear, and K is equal to 1.92 times 10 to the minus 3. So in I think all three of these questions, we'll see in a moment, we are using the integrated rate law to get a K so that we can get a half-life or some combination thereof. And so now I can just plug my K in here, and my T1/2 is equal to 0.693 divided by the 1.92 times 10 to the minus 3. And I get a half-life of 361 hours, which is the correct answer for that question. Right? The next one we're going to do is number 7. So let's just extend the page. Number 7 in the ACS book on page 61 says, turn to it, the half-life, so they give you the half-life, okay? So this is going to be number 7, same page. So the half-life is equal to 22.7 seconds at a particular temperature. How many seconds, so they want time, are needed for the partial pressure of cyclobutane to decrease from 100 millimeters of mercury to 10 millimeters of mercury. So this is like a reverse of the previous problem. We are going to use the half-life expression first to get our K, and then we're going to solve the integrated rate law, and it says first order in the problem. We're going to solve the first order integrated rate law to get our time. All right, so again, we're given two different concentrations and some time information, so that tells me integrated rate law. All right, but first let's use the half-life expression. T1/2 equals 0.693 divided by K. So K is equal to 3.053 times 10 to the -2. Okay. Now we're going to plug that into the integrated rate law. So it is the ln at time t, which will be 10, equals minus 3.053 times 10 to the -2 t plus the ln of the initial concentration, which in this case is 100. All right. So if we do our natural logs, we get 2.303. See, that's where that 2.303 came from in the Arrhenius equation. Going from a base 10 to the natural log. Negative 3.053 times 10 to the -3t plus the ln of 100, 4.605. Subtracting the 4.605 from both sides, I get negative 2.302 equals the negative, and the negatives go away. Dividing both sides by the 3.053 times 10 to the -t, I get time of 75.4 seconds, which is the correct answer for this question. All right. Okay. So the last one we're going to do from the ACS on this section is number 26 on page 65. All right, so 26 on page 65. Page 65. Now I think what I'm going to do is get us a new page here, so hold on just one sec. There we go. A little more room. It's getting, as I extend that page, it gets really skinny. All right, so number 26, page 65. Can't have everything out on my lap and on my desk all at the same time. Really hard to do. All right, so number 26 says, the rate of conversion from cyclopropane to propene at a constant temperature is first order. Okay. From the information in the graph, and they give you a graph, which statement about the half-life of the conversion reaction is true? And they're essentially, in the answers, essentially they're telling you what the half-life is. Okay, so you will have to take this graph and the fact it's first order to get a half-life. All right, well, what the graph shows is, and I'm just going to kind of, you can look at it on in your ACS book, it is pressures versus time. Okay, so I've got different pressures versus time, so essentially I have different concentrations. Okay, and it's got, several points. It's not a straight line. All right, so this is different pressures, different concentrations, and time information. Again, asking about half-life tells me we're going to use the integrated rate law and the half-life expression. So one more time, but this time you have to get the information off the graph. So what I did was I took this first point right here, and I got a pressure and time information, and then I took another point And so I got the, I'm sorry, I took that point and the initial concentration. So I had an initial and a time t. So here's my time t. Here's my pressure, okay, at time t. And here's my initial. And I use the integrated rate law, first order, to get my K, so then I can plug in and get my half-life into the first order half-life equation. Okay, so what I did is not easy. The graph is, the points, none of the points are, fall directly on lines or in the corners of the graph. So I took the first point here and read that pressure to be approximately 43. Okay, so this was 43. That's what I called it as 43 millimeters of mercury, and the time was 100. So pressure equals pressure, time equals 100. Okay, off of the axis here. And I plugged that information and the initial, again, the initial not following, following nicely, in terms of numbers, but I took that to be 56 millimeters of mercury at time 0. Okay, so I'm using those two pieces of information, integrated rate law, to get my K, because I need that before I can get the half-life. So I took the natural log at time t. Time t is the 100, so 43 equals minus K times my time, which is 100. Again, that is the time right here for this point, plus the natural log of the initial concentration. And again, I had to eyeball that. I took it as 56. All right, so 3.761 when I take the natural log of 43 minus K times 100. Natural log of 56, 4.025. Subtracting both sides. So here's the third problem, all asked slightly differently, information given slightly differently, but we're doing the same thing. And my K comes out to positive, of course, 2.64 times 10 to the third. And my half-life expression, first order, over that K, and I got very close to the right answer, even eyeballing. I got 263 seconds, which is approximately the answer for B. All right, so I've looked at all the ACS questions, eliminated a couple. I'm making sure with this wrap-up that you are prepared for any of those questions. All right, I'm going to pause and get ready for our next set of problems. And the next problem that I want to talk about just briefly, because I'm going to do some more problems, is this one here. This is the one that I realized when I went back through the notes when I was picking problems, that the data that the problem refers to had been left out. So this data was left out. Could not find the exact data that corresponded to the explanation, at least on one part. So I changed the explanation slightly to reflect this data, all right? But I want to just kind of walk, all of this is worked out step by step in the notes. I believe it's pages 38 and 39 in the notes volume 2. But I just want to kind of, point you in the right direction and then have you refer back to those notes where it's worked out for you. So then I can go on and work some other examples that you don't have worked out for you. So now the data is there. I uploaded a new version of the notes. So that may not match what you have, but that's okay. So the first thing we have to do, you're given an overall equation, you're given some data, okay? And then you have to determine the order of reaction with respect to each reactant. So this is the method of initial rates. Okay, that's what we're using, method of initial rates. Make sure you explain your reasoning. It's an AP question. And give the rate law. Okay, so we're going to go through that quickly together and then remind you how to do this. Remind you about coefficients and rates of appearance and disappearance as given by the overall chemical equation. And then there's a mechanism. So we're going to do lots of those after I go through this, okay? All right, so we've got two reactants, the ClO2, and that did not superscript, and OH minus, subscript. And you're given two different concentrations and the rate. So that didn't copy over as well as it should have, but what you want to do, like for OH minus, we want to use the two experiments where the other one is held constant. So I went from 0.0468 to 0.0936. So to me, that looks like a doubling. And what happened to the rate? All right, so that's what we have to do. So I'm reminding you that for the method of initial rates, take what happens to the concentration. Always put the larger one over the smaller one. And then do the same thing with the rate and see, so see what you get when you do that, and then do the same thing with the rates and compare. So 0.0936 divided by 0.0468, and that is 2. So then you do the same thing using the same two experiments. So now I'm going to take 0.0636, that's my rate, over 0.0318. And that's also a doubling. So the order for OH minus is 1. Okay. So when I write my rate law, this is what we're after. Rate equals K times, we still have to determine the order of reaction for the ClO2, and there's no charge there. All right, take that off. Should not be anything there. Okay. And then, so we haven't just determined that one yet, but we just determined that hydroxide is a 1. Okay? Now, do the same thing for the ClO2. Find two experiments where it changes and the other one stays the same. So that looks like experiments, so you want this one to change, this one to stay the same. So if I take experiments 1 and 3, OH minus is staying the same. What happened to the ClO2? Well, it's exactly the same ratio here, right? Between experiments 1 and 3 for the ClO2. So I am doubling the concentration. What happened to the rate? Larger one, 0.127, over the smaller rate, 0.0318. Now, if you put experiment 3 on the top, divided by experiment 1, you have to do the same thing to the rate, because it might actually go down. So experiment 3 over experiment 1, so 0.127 divided by 0.0318, and I end up with 4. So, reminding you how this works, I am taking the concentration and I am doubling it. What do I need to raise this to end up with 4? Squared. So x is 2, and it's second order with respect to the ClO2. So it's overall third order. So determine the value of the rate constant. Remember how to do that. You take one experiment. Experiment 1 is just as good as any other. What's going on? Experiment 1, and plug in your information, your rate. Plug the rate in here, plug in your concentrations, and get your K. All right. The last thing I want to do that's done for you in the notes is let's look at this mechanism. We have a rate law, okay? That rate law must correspond to the slow step in the mechanism. The slow step is what determines the rate of the reaction. So that's what it's asking here. Which step is the rate determining step? Show that this mechanism is consistent with both the rate law and with the overall stoichiometry. So this second part of the question is add these three equations up and make sure they come out to the overall chemical equation. All right? And again, that is done for you. Now, this whole rate law, rate determining step thing, y'all seem so confused about that. Step 1. If I write a rate law for step 1, it does not have OH minus in it. OH minus is in the rate law. So step 1 cannot be my rate determining step. Okay? Step 2 has OH minus in it, and so does step 3. Now, But steps 1, 2, and 3 have intermediates in them. All right, so we have to do that little, get rid of the intermediate thing. So let me extend the page. This is getting so small. Tell you what, let me exit this, and I'm going to pause to get this where we can see it better. All right, so here is our mechanism where we can see it better. We've already determined that since OH minus does not appear in the first step, the first step cannot be rate determining. The first step gives me the right order for ClO2. If I were to write a rate law from step 1, and remember we can do this from elementary steps, it would be, and that's one approach to doing this type of question, is just to write the rate law for all the steps. The rate is equal to, for the first step, it is equal to ClO2 squared, because I've got 2 of them. Okay, so, but it doesn't have OH minus in it, so the first step cannot be rate determining. Writing the rate law for the second step, rate is equal to Cl2O4, which is an intermediate, so we're going to have to do some substituting, but my OH minus does come in and it has the right stoichiometry. I need to replace this with what it is equal to, so I go up to the step where it is produced, and I say that the concentration of Cl2O4 is equal to this. All right. Now, what we're actually doing here is, because this first step is, I'm not going to confuse you anymore. I am putting the Cl2O4 equal to what it is on the other side. So if I do that, I end up with the correct rate law that agrees with what was determined experimentally. Okay, let's just do it for step 3, just so we've done it. Okay, so if I write the rate law for step 3, it also has an intermediate in it. But the problem with step 3 is it also has OH minus, is you're going back to step 2 to get this, and you've got an intermediate there. So what I can do is HClO2 is equal to Cl2O4, but we know that that is equal, and OH minus, okay, right? That is equal to this. No, hold on. Erase. Do it step by step. Going back to where this was produced, it is equal to this times this, but this has to be rewritten as, like I did up here, to be this, okay, but it's still times this. So when I put that back in here, I end up with a rate law that does not agree with the experimental rate law, because it would have the OH minus as second order as well. So the second step agrees with the experimentally determined rate law, so the second step must be the slow step. The rate of the reaction is dependent on the slow step. All right, I'm going to pause and we're going to do some more of these. What I have here are a number of mechanism questions that I got off the internet. Those 2 worksheets that I have for you also have questions just like these. Okay, so we're going to just do several of these mechanisms, writing the rate law from the slow step. Okay, so here's the overall reaction. Here's the mechanism proposed. It says write the rate law based on this information. So we are going to use the slow step only, and we're going to write a rate law from that, using that elementary reaction, but we have to be careful in that we don't put an intermediate in. When the slow step is the first step, you don't have to worry about that because you can't have produced any intermediates yet. So the rate for the slow step in this mechanism, which is step 1, is K times AB squared, because I had 2 ABs. Okay? Which species is an intermediate? So what is produced and then consumed in the next step? And that would be AB2. Okay, at this point, pause the video before I go through any of the others and try them yourself, and then you can come back and check your answers. Okay? All right, so number 2, we're going to do the same thing for each of these questions. Slow step is the first step, so we're going to write a rate law based on that slow step. No worries about intermediates. So it's NO2 times Cl2. All right, and that's my rate law. Which species is an intermediate? What is produced and then consumed? And that would be Cl. Produced right here and then consumed. Okay. Alrighty, number 3. Now, this time I got a slow step. That's the second step, so very well may have an intermediate, but let's go ahead and write the rate law. K times X2 times Y. In each of these, you're given the overall equation. X2 does not appear in the overall equation, so we already know it's an intermediate. And I've got to use this first equation to put in what X2 is equal to. And so that is going to be 2x Okay, well 2x is the same thing as x and x, so this is going to be rewritten as x squared, okay, because I'd be using the coefficient as an exponent, okay. So then my rate law is equal to k times x squared, which is in the original, x is in the original equation, times y. Okay, y to first word for y. All right, last one here, number 4. Again, fast step first, slow step second. So we'll write the rate law based on that slow step. It probably has an intermediate in it. H2 and then times I, and it would be squared, okay? Now I is equal to I2, well, 2I is equal to I2, so when I rewrite this, I is my intermediate, produced in one, used in the other, then it's going to be essentially 1/2 I2, okay, with the stoichiometry. And then if I square that, I end up with just I2, okay. So the rate law is H2 times I2. Probably didn't need to go through this whole thing, but for completeness I did, and you would get the same answer whether you did or didn't. All right, so substituting in for my intermediate, this is my rate law, I is my intermediate. And then this last question says, why can't you tell what the rate equation is just from looking at the overall reaction? The overall reaction does not tell you what is the slow step. Most reactions do not occur in one step. And the slow step is the thing that determines the rate, and that is why you cannot. So you must know the slow step in order to write the rate equation. All right, I'm going to pause, and we're going to get ready for one big wrap-up question, and then we're done. Here we go, last question. We are going to do the method of initial rates one more time. We're going to write the rate law and determine the value of the rate constant. Then we're going to do the whole stoichiometry thing. And then we are going to identify which of the following mechanisms are consistent with the rate law. And this is not the last question. I have to do number 19C as requested by one of your class members. So that'll be our last problem, but it's quick, really quick. All right, so again, our little pasting didn't come out, but this is our A concentration. These are our B concentrations. These are our rates. So in this question, I'm going to start with A, since I do have 2 experiments where B is held constant. I don't have that for A, but we'll worry about that when we're done. So here B is being held constant, so I'm going to take the 0.75 for A over the 0.25, and I believe you can see that that is 3, so I tripled the concentration. Now I'm going to do exactly the same thing with those 2 rates. So experiment 2 over experiment 1. So 1.3 times 10 to the minus 3 divided by 4.2 times 10 to the minus 4. So what happened to the rate, okay, at the same time? I don't have this one worked out in advance. Okay, so I end up with, 3 again, okay? So a little over about 3.1, so 3. And so it's first order for A, okay? Yes, first order for A. All right, so I'm going to say rate is equal to K times A, and A is to the first, and now we have to do B. Now, this is what I'm going to have to do. I really am going to have it as an X, and I'm going to take those same 2 experiments. No, I can't do those same 2 because B is being held constant. So let's go with 1 and 3, okay? And plug in and see what happens to the concentration of both A and B, and what happens to the rate when I change them both, okay? So between experiments 1 and 3, let's go ahead and do the rate part. 5.3 times 10 to the minus 3 divided by 4.2 times 10 to the minus 4, and that is equal to, that is equal to 12.6 So what happens to the concentration? Well, between A goes from is 1.5 divided by 0.25. So I know that I'm going to take 6 and I'm going to raise that to the first power. Then what is then the same? What happens to B is 1.5 divided by 0.75. So I doubled B. So essentially, I am increasing the concentration by a factor of 12. 6 times 2 is 12. I don't know what this is, but it can only be 1 if indeed I am going to end up with a rate, increasing my rate by about a factor of 12 as well. So my rate law is first order with respect to both. Okay. All right. So x is equal to 1. Determining the value of the rate constant, we're just going to take one of these experiments and we're going to plug the information in, okay, and solve for K. So 4.2, and do it right here, 4.2 times 10 to the minus 4 is my rate. That is equal to K times 0.25 raised to the first times 0.75 raised to the first. And I end up with a K of 2.24 times 10 to the negative 3. And my units are, I've got molarity squared here because of the firsts. Okay, molarity times molarity. It has to be molarity to the over seconds. So K is molarity to the minus 1 seconds to the minus 1. Because when I multiply that times m squared, I end up with my rate of molarity over seconds. All right. Now, last part. Oh, C. Determine the initial rate of change of A in experiment number 3. Now, you have to look up here at what you're given. What you're given is the rate of formation of C. Well, how do C and A compare? the rate of disappearance of A is twice the rate of appearance of C. So I am going to take, in experiment number 3, I'm going to take the rate of appearance of C. It is 5.3 times 10 to the minus 3. And I'm going to multiply that times 2 to get the rate of disappearance of A. And it's going to be negative because I'm looking at a reactant instead of a product. And I get 1.06 times 10 to the minus 2. Negative 1.06 times 10 to the minus 2. All right? Okay, now we have a rate law. Here it is. I need to pick which mechanism corresponds to that rate law. Okay? Number 1, it has A and B in it, but it's not, the first step has A and B in it, but it's not the slow step. This is the slow step. The slow step has an intermediate in it. So I can put so let's write the rate law. Rate equals M, but I'm going to go ahead and substitute what M is equal to. M is equal to A times B. All right. And then I also have to put another A in. So that would be A squared, and that does not go with my experimental data or my experimental rate law. So mechanism number 1 is disqualified. Number 2, slow step, writing the rate law. Rate equals K, of course. K, and then substituting in for M from the first step, I would have B, and then that's what M is, and then times A. So that's looking pretty good. That is my rate, that's my mechanism that corresponds to the rate law. But let's rule out our last one here. Slow step. Rate is equal to K times M. But M is A and B, so it's A and B. But then I have to put in another A. So this one is ruled out because I get A second order for A. So this mechanism is ruled out, and it's number 2. That is our mechanism because the slow step corresponds to the experimentally determined rate law. Right? Now I'm going to X out of this and pause and get ready for that last small question. All right, our very last question is 19C from chapter 14. And 19 is just like number 20, so I'm sorry I don't remember the name of the student who asked me to do this question, but number 19 is just like number 20, which was the very first question we did in chapter 14 as a practice. So what they're asking you to do, so they gave you, in both those questions, they gave you moles of A and time. Okay, different moles of A, different times. And I remember we went through this step by step in class, okay, and that's what A and B on 19 is asking you to do, same kind of thing. Now they did give you a volume in 19, which they did not in 20. So the volume of the flask is 0.1 liters. But again, in number 19, they only give you moles of A, and the overall equation is A produces B. And we went through all of that in number 1 on the practice, which is number 20 in your book, in class. What they're asking you in C is it's asking for the rate of appearance of B from between time from 30 minutes, from 10 minutes to 30 minutes. So between 30 and 10, they want you, or 10 and 30, they want you to calculate the rate. Okay? Well, in A and B of this question, you would have, got your change in concentrations of A, and you would have gotten your change in concentrations of B, which is what we did in class. Okay? So then you generated this, just like we did in class. So what you want for C is you want the change in concentration of B over the change in time. And that time is between 10 and 30. between those two pieces of data. So at time at 10, your concentration that you would have figured out for B was 0.014 at time 10, and at 30 it is 0.029 because you're building product, okay, right? So it is going to be 0.029 minus 0.014, but that's moles, and they want a rate in molarity, so you're going to divide that by 0.1 liters. And then you're going to over 30 minus 10, so over 20. And when you solve that, you end up, and this is in minutes, and they want it in seconds, which is the normal rate time. So you've got to multiply this times 60 minutes. 1 minute over 60 seconds. All right, so not only do they want it, they don't want it in moles, they want it in molarity, and they also want the time in seconds. So it is, minute needs to be on top, 1 minute, 60 seconds. So you got to divide by 60. And when you do the math, subtract that, divide by 0.1, divided by 20, and then divide by 60, you get the answer, which is 1.3 times 10 to the minus 4 molarity per second. And that is going to conclude a wrap-up for a very long and full chapter. I don't know if there's any other chapter this semester that has this much information in it. So we are done, and I didn't want to do that. And